Hi everyone. In this Connect with Networking video, we're going to continue our discussion of Chapter 7, Wireless Local Area Networks and Local Area Networks. Let's go ahead and continue. We last left off talking about wired Ethernet. Let's shift our focus now to wireless Ethernet, which you have probably called Wi-Fi your entire lives. As an aside, the term Wi-Fi actually doesn't mean anything. It's based upon the old abbreviation for high fidelity stereo, but in this case, Wi-Fi does not stand for wireless fidelity. It's just an acronym that sounds good. So Wi-Fi is a family of standards that was developed by IEEE, much like the 802.3 standard for wired networks. But the abbreviation is 802.11, which you've probably seen throughout your lives as you've configured your various wireless devices. And Wi-Fi uses radio frequencies to transmit signals instead of cables, which obviously has some significant benefits. If there are situations where cabling is impossible or undesirable, Wi-Fi is a great fit. Particularly places where the terrain is challenging, wireless might be a good choice. Or a building construction doesn't allow for modification. If you're a renter, or it's an old building, or it's built out of materials that don't allow for cabling, Wi-Fi might be a good choice. It is often much more economical, but it does have some downsides in terms of security and in terms of attenuation, where the farther away you are from a network device, the worse your signal and your bandwidth might be. The device that a client connects to over a wireless Ethernet is called an access point. Most of you are probably thinking about wireless routers when you think about wireless Ethernet, but a wireless router is actually a router or a switch that also has a built-in access point. And that is common at the consumer level, but for enterprise level devices, often access points are standalone devices. So if you look around the building in Maze, you will often see wireless devices that are on the walls or ceilings in our building and in our classrooms. And those are standalone access points that don't actually have any routing or switching. They just receive and broadcast wireless signals. Many access points use omnidirectional antennas because most of us do want our access points to provide a sphere of connectivity. But in some cases, the antenna will be directional, where we're sending a specific signal from one place to another, much like microwave antennas. Access points can be either active or passive. An active access point is constantly sending out a broadcast signal announcing its location. A passive access point is out there and will respond to a ping, but doesn't actually announce itself. In order for a client to connect to an access point, it has to have a wireless network interface card. Again, these network interface cards are now usually integrated into the motherboard of your various devices, whether it's a laptop, a desktop, a tablet, or even a phone. When we move from wired to wireless Ethernet, the modern topology is a physical star where every device on the wireless network gets its own frequency set. But the logical topology is actually a bus. All of the radio signals that are out there are easily received by any antenna. So there's nothing stopping a device from listening in on the signal that you're sending or receiving to and from an access point. So everything is sharing the same space, which does mean that you need to add an additional component to secure your communications over a wireless network. And that would require something like encryption, which we'll talk about in a later chapter. Because all of the devices on a wireless network are on a logical bus, where they share the same space, we use a slightly different set of protocols for media access control. We still use the carrier sense, where every device can listen to other devices, multiple access, where multiple devices can connect to the network. But instead of collision detection, we adopt a collision avoidance algorithm. And there are two ways that we pursue collision avoidance for wireless networks. One is called the distributed coordination function, and the other is called the point coordination function. For collision avoidance on a wireless network, the easiest way to manage this is a distributed coordination function, where all of the devices that are connecting to an access point have the ability to listen to all of the other devices that are connecting. They all physically listen to one another, They wait until there is silence in the radio space, and then they wait a random amount of time longer before they start to transmit. So this is similar to the collision detection we saw for wired, but rather than broadcasting immediately and perhaps having a collision and then starting a random number generator before you rebroadcast, collision avoidance using distributed coordination function uses the random number generator as the default behavior. So when things are silent, every device that wants to communicate waits a random amount of time before broadcasting, and whichever device happens to have the lucky lowest number gets to broadcast first. So this tends to avoid collisions in the first place. Every frame in a DCF model will be sent using stop and wait ARQ, where you send a packet, you wait for acknowledgement, and then you send another packet. This means there is a somewhat longer time for message frames to be sent and received. One of the downsides to distributed coordination function is what's called the hidden node problem. If two devices are at the far outer edges of an access point's range, and they're on the opposite sides of that range, they might be able to see the access point, but not actually be able to see or hear each other. Even though they're behaving themselves using the distributed coordination function algorithm, where they listen and then they don't broadcast unless nothing is happening, and then they wait a random amount of time before they start to broadcast. Because they can't hear each other, they might start broadcasting at the same time. So this is called the hidden node problem, and the way that we solve this is by moving from a distributed coordination function to a point coordination function. A device that wants to communicate first sends a request to send signal to the access point, waits to receive a clear to send signal, and then begins transmitting. In modern Wi-Fi networks, the request to send and clear to send channel is separate from the rest of the channels for actually sending data. So you can effectively raise your hand and ask to speak without interrupting someone else who is communicating on the network. And then the access point will eventually call on you to be the communicator, and then you can use the actual bandwidth available for communication without interfering with any other devices. By giving control of access to the central access point, we avoid the hidden node problem, but that does mean that the access point has additional responsibilities. The frame for 802.11 is slightly different than what we saw in 802.3. The biggest difference is that it actually has 4 address fields instead of 2. It still has the original origination and the final destination, but it also has additional address spaces for allowing access points to communicate with other access points and other devices. So there can be some intermediate addresses included in the frame. Wi-Fi devices transmit on a variety of different frequencies. Historically in the United States, our Wi-Fi networks have been using either 2.4 gigahertz or 5 gigahertz. The higher the frequency, the more bandwidth available, but we tend to see more attenuation. Higher frequency has trouble getting through walls and floors, so while it's faster, it may not have as great a range. I'm recording this video in fall of 2020, and where we currently stand is likely using 802.11ac or 802.11ax. One of the recent changes we've seen in the Wi-Fi world is we're referring to Wi-Fi using Wi-Fi 5 and Wi-Fi 6 instead of the 802.11 nomenclature. If you see something that says Wi-Fi 5, that's actually 802.11ac. If it says Wi-Fi 6, that's 802.11ax. And while this slide says estimated 2019, it's really started to be adopted here in late 2020, and it is continually evolving. There is an 802.11ad standard, which is meant for very short distances between pieces of equipment, like your television and your stereo speakers. And so it is not something you see commonly used in the Wi-Fi space for communication. The biggest downside to wireless Ethernet is the security concern. Because every device on the network shares the same space, we have to make sure that we add additional protocols to protect the signals that every device is sending and receiving. One of the original protocols for wireless security was called Wired Equivalent Privacy, or WEP. It was very, very poorly designed and actually is very easy for modern devices to bypass. If you have an older device that has this as the only option, don't even bother. It's not providing any security whatsoever. Modern security requires either WPA or WPA2, which is also 802.11i from the IEEE standard. And this provides a high level of encryption of your signals back and forth from your client to your access points, and does provide quite a bit of security. One other thing that you can adopt on your personal networks is called MAC address filtering, where only certain hardware addresses will be allowed to connect to your router. This is fine for preventing casual users from accidentally connecting to your wireless network, but it is also easily bypassable by someone that is determined to actually access your network. When we think about designing a local area network, there are a couple of things that we should consider. We should always adopt the fastest, stable technology, cost permitting. If you were buying a router today, I would absolutely suggest that you buy a wireless router that has either 802.11ac or 802.11ax. If you are building a network at your house, I also recommend that if you can, you wire everything possible. And I know for some of you that probably sounds like old school design philosophy, but think about it. Every device that you wire into your network is one less device that's competing for the same shared wireless space. And as a consequence, the devices that are using your wireless network have that much more bandwidth to work with and that much less interference to contend with. So as much as possible, wire everything, which is always faster and more secure, and then use wireless using the most up-to-date protocol that you can afford. Wireless local area network design is a challenge because we are dealing with all sorts of potential interference objects. In the enterprise space, usually the design of a wireless network requires a site survey to determine the kind of coverage we require, what types of interference we might be dealing with, and then where we actually can securely locate hubs and switches and access points and power sources so that we can actually provide a network for our users. This first picture on the top left is an ideal situation where we place access points throughout our building that just barely overlap and never share the same channel where they overlap. So you can see alternating 1 and 6 and 11 channels in these perfectly aligned circles so that as you move through the building, you are never without wireless connectivity. This is unlikely to be what the actual building layout looks like, because you might want to be putting an access point where there is no accessible electricity, or where there's a pole or a doorway or a window, and so you have to move things around. There might be interference, which causes one of these circles to not actually have its full range available to it, which means you need to shift everything around a little bit. So this is certainly an idealized situation, but this is probably not what an actual wireless network looks like. And keep in mind, we're normally not dealing with two-dimensional space. The lower right-hand picture shows you how in a 3-story building, you might have to place access points in various locations for both up and down and side to side. There are lots of things to consider when you're designing your local area network. Some local area networks may require load balancers. This is where we create a series of devices that are effectively identical to serve up content to our customers. And then we would build a network that automatically routes a particular customer's request to the next available server in our server farm. So you can imagine the first request going to the very top computer, the second request going to the 4th computer to keep the various network devices as free as possible, the third request going to the 7th computer, and then 258, and then 369. And then, of course, the next available device going to the next available server. So load balancers would allow us to spread out the signals across our network in the most equitable way possible. The other thing we might deal with is virtualization. And you've been playing around with virtualization in your homework exercises, where we're using Amazon's web services to instantiate a virtual client that you can manipulate. And I've used the same service to create a virtual server in Amazon's services. A single hardware device can act as one or more servers on a network, and this gives us a lot of flexibility. Different networks will require different levels of security. There are lots of businesses that actually will opt to skip Wi-Fi entirely because of the security concerns. We happen to exist in an educational environment where accessibility is highly valued and security not quite as much. So you have access to wireless networks throughout the campus. If your local area network is not performing as you'd like, there are a couple things we can do to improve the throughput. The first step would be to identify where the bottleneck is actually occurring. It's possible that it might be a particular device on your network that is causing the bottleneck. So if your servers are operating at more than 50% of their capacity, it's probably time to upgrade their CPU or their memory. It might also be time to upgrade their storage capacity. Similarly, if a particular client is very slow on your network, it might be time to upgrade its network interface card or add some additional memory or storage space. And the same thing would apply to our various network devices. If the slowdown is your circuit, you can certainly increase the speed by moving from twisted pair to fiber optic, or adding additional circuits between various devices, or even moving your access points or your servers or clients to different locations to provide faster connectivity from one place to another. You may even consider network segmentation. The idea here is that every device might be connecting to a single network device, and that network device is getting overwhelmed. If we spread our network out and give our networks separate connection points, the amount of traffic flowing into each individual network device is reduced significantly, and the overall performance could improve dramatically. An alternative to adjusting our hardware or our circuits would be adjusting the kind of traffic and the amount of traffic that's flowing across our network. Maybe instead of changing our network structure, we can change where we store our files. If a client doesn't need to access the network to access the files it needs, there's less traffic flowing across your network. If your device can access files during off-peak usage, so late at night, that might also improve network demand. Here on campus, we, at times of peak demand, throttle certain types of traffic. So if you're trying to watch videos on your computer in a campus dorm during finals week, you might actually not get as much throughput as normal because the administrators on campus could be throttling that traffic to make sure that crucial traffic is flowing through our network at adequate speeds. And you can do similar sorts of things on your personal network, where you throttle certain types of traffic to allow for priority traffic to flow more freely. The implications of this chapter for management are fairly basic. The kind of equipment we use on an enterprise local area network is quickly becoming commoditized and is very similar to what you might install on your small office or home office. Most small offices have moved to adopt primarily wireless because of its convenience, and the protocols we use for security are more than adequate. That said, I still advocate using a wired network whenever possible to give yourself the most available wireless bandwidth for devices that must use your wireless network. We will continue to see dramatic growth of Wi-Fi enabled devices moving forward into the future, so the more bandwidth we can provide to them, the better. That's it for this chapter. Thanks so much for watching. See you next time.